did you do all of these in one page? Did it wrong? God.
So, I mean, you did very well actually, so I feel really bad. Maybe I should have assigned something harder, although it seems that you might have worked in groups. Some answers are similar, although, of course, how many types of ways to solve it. There are some questions that you solved absolutely right, but could be done with greater ease.
Problem 8 was brute force. So what's another word?
Brute force, a lot of it. I mean, you are very strong with brute force, right? So
was any other way to do it?
I actually, I don't want to spend a lot of time on it, but maybe, actually what I'll do, I won't spend time on it today. If you want to talk to me in office hours, I might consider writing my own solutions for those, for all the questions or for a select number of questions. But, yeah. All right, so let's try to move on. So here is what we talked about last time. We spoke about cross ratio. By the way, you all know the new homework assignment. I didn't yet set up the date, but you know, it might be a little bit difficult. Maybe not. I mean, you're a very smart guy. Right? Maybe it's very easy. I mean, I feel like, my God, what am I wasting your time for?
Since that's the definite date, 16?
I didn't say anything yet, right? I'm gonna say a definite date. I assume give it to me in like a week and a half, 2 weeks, right? Just tell me how you are doing with it. If you are stuck somewhere, don't panic, don't worry, right? Okay. It's a graduate class. I don't want to give you trouble. I don't want you to give me trouble. All right. So cross ratio, and you remember what cross ratio is, right? It's what? It is, in your words, what is cross ratio? Yes?
4 points can be mapped to 4 images distinctly and only have the cross ratios invariant.
Well, I mean, that is already using cross ratio, right? So let's just, so you're right in essence, right? But think of it very, very simply. What is cross ratio? It is a Mobius transformation that unfolds the circle onto the real line. Okay, that's how you can think of it. It's just some sort of operation that will unfold a circle and stretch it into a real line. And the reason you like it is because real lines are straight, right, and horizontal, and a lot of nice things about it. A lot of easier equations, and it allows you to just figure out how to move from one circle to another with greater ease. So cross ratio is just a Mobius transformation. That there is a circle, and you can specify, what's more, you can specify 3 points on that circle. Specify any 3 points on that circle. Let's call this Z2, and the reason I call it Z2 is because I follow Conway's notation, although my cross ratio is slightly different from Conway's cross ratio. It's going in the opposite direction. So we take Z2, we take Z3, and we take Z4, and what does it do? It will carry it onto a straight line. And what will be true about that straight line is that I chose just very convenient points. The reason I chose 0, 1, and infinity is because those are the ones that it's easiest to write equations for. So what you do is you have 0, so Z2 will be carried to 0, Z3 is carried to 1, and to infinity, Z4 is carried. So you see, specifying the points in this order, so notice I specified it as Z2, Z3, Z4. I specified orientation. Right? So you see, if you have a circle, if I have 2 points, I don't know which way to go. To go one way here or the other way. So if I specify 3 points, now it gives me the consecutive sequence that I should visit. It gives me an orientation. In this case, I gave it a counterclockwise orientation. I could have given it a clockwise orientation, depending on how I distribute Z3, Z2, and Z4. Okay? So in this case, this has a counterclockwise orientation. And that orientation will, whatever the orientation you have here, will correspond to what? So you can see that Z2 is carried to Z3, so we're moving like this. Okay? Yes?
I know we had this discussion last time. Can we have just 2 points to give the orientation, or we have to have 3 points?
You have to have 3 points. On the circle, you have to have 3 points. And you can now think of even a straight line as a circle.
Right.
You understand? Even a straight line is a circle. It seems that it's enough to give 2 points, but then you would be mistaken. So just, if they were on a line, let me just draw, maybe possibly they are on the line. Imagine what happens if they are on the line. This is now an infinite circle. So this line, if you image it to the Riemann sphere, it would be a circle that goes through the North Pole. It touches the North Pole at one of the points. Okay? So now suppose that you specified something like this. You specified Z2, and then you say Z3 is here. So you would say, well, I gave an orientation. It seems that from Z2 to Z3, I just go like this. But now you are wrong, because it's a circle. Because the way I can get to Z3 now is in 2 ways. I can either take the short way or the long way. I can go this way and around. Do you see that?
Got it.
So it's now, you see, infinity is connecting those points.
Got it.
So you cannot give an orientation without specifying the next point. You see, I mean, infinity is no longer as infinite as it seems, right? It's just, all it is just it's on a circle, it's compact, right? The Riemann sphere is compact. All the distances on the Riemann sphere are finite. Okay? So in essence, you can think of going, pretty much, you're always going in circles. Okay? So yeah. That is what it is doing, and we gave its formulas. I don't want to repeat the formulas. And one important thing, I mean, just also one important property of Mobius transformations, that by the way will be true not just of cross ratio, but of any Mobius transformation. You can specify what it does to any 3 points, if such a thing will exist, of course, if there is a Mobius transformation that exists. This one we were able to give explicit formula, and therefore we know that a Mobius transformation that carries the entire circle and those 3 points in this fashion does exist. Now, how do you see? All I need to know is just how to carry those points onto the corresponding 0, 1, and infinity. Because once I know that, we proved that the image of a circle is another circle. So the only circle that goes through those 3 points, the circle is determined by 3 points. Right? The only circle that will go through those 3 points must be a straight line. So that takes a little getting used to. You can read the geometric interpretation, but it's a little bit wordy in the three-strand book in Visual Complex, or you can read the more compactified version in Conway that you have on the website. So very important property is invariance, right? The invariance is this. We know that the Mobius transformation that is written here, this is the way you write this Mobius transformation, you can say CZ, you don't even need to say CZ, and you can write something like Z, Z2, Z3, and Z4. Okay? This is now, you can just go with Z1. That's why I said Z, Z4. Okay? That's the transformation, that's just a label for it, and that tells you what it's doing. And we gave concrete formulas. So very important invariance properties is that if T is any Mobius transformation, if it's any Mobius transformation, then you would observe that T of Z, T of Z2, T of Z3, and T of Z4 is equal to Z, Z2, Z3, Z4. That will always happen. Now, the reason for this is actually rather simple. If you interpret what this is doing, this is a composition of another cross ratio with T of Z. And if you just now see the composition of maps, what you see is that you begin with this circle, and you go through an intermediary circle, and you end up exactly on the same line with the same point. So if you ignore the intermediary circle, then you see that it must be the same function. Yeah? Good. So I'm not going to repeat the proof. Maybe on the exam you will repeat it. Right? That's an easy proof. Yeah. So now using the fact that I can take any 3 points and map them on the real line, I can actually now move from one circle to any other circle, and that's the next proposition. Okay, that's how I prove that I can move from one circle to another. I can always take a circle, take any other circle, and there is a Mobius transformation that moves the circle to the other, and moves it in a way that it moves the 3 points where you specify them, where you would like them to go. So that's the proposition that we're proving now. If Z2, Z3, Z4 are distinct points in this, and you remember what this is the Riemann sphere. Okay, so one of them could be infinity, and W2, W3, W4 are also distinct points of the infinity, then there is one and only one Mobius map S such that S of Zk is equal to Wk. Okay? Proof. First of all, existence. So let the cross ratio Cz be just given by Z, Z2, Z3, Z4. Okay? So again, I want to remind you that if I specify any 3 points, and if I specify any 3 points, they must be on a circle. Where if it's a straight line, that's the circle that goes to the North Pole. Okay? So this map is doing what? It's carrying Z2 to 0, Z3 to 1, and Z4 to infinity. So this is carrying some circle containing the points Z2, Z3, Z4 onto the straight line, and it specifies which points are moved where. So we have one map CZ, and we will have another map R of Z. And R of Z is equal to Z, W2, W3, W4. In terms of a picture, here is what we have said. We have one circle, and that circle contains, I don't know in which order, I like to write them, maybe I'll do it this way. Z2, Z3, and Z4. So the circle has a counterclockwise orientation, and maybe the other circle I'll give it a clockwise orientation, just for the fun of it. So we have this circle. What's happening to it? The map C unfolds it. There's the 0, 1, infinity, and moves it counterclockwise. Okay, that's what C is doing. Now what is R doing? Let's say that the points are specified like this. So I have W2, and then I have W3, and then I have W4. So in this case, what can you say about the orientation? What's the orientation here? Clockwise. You move from W2 to W3 to W4. You see? It's basically you look at the circle and you need to walk around the circle in such a way that that if you're starting at W2, the next thing you see is W3, and the next thing is that you see W4. And that tells you that we're moving clockwise. Okay? So we're moving now this way. So in essence, what this theorem is gonna work out is that I have two circles. I have 3 points on each circle, and I gave them orientation. And now I'm gonna see what's happening. What is R doing? R. Now, when R unfolds it, is gonna be the unfolding? Is it gonna be in the right direction of the real number line, or in the left direction of the real number line? So we have those arrows that are moving now here. Here they are moving. You see here they are moving counterclockwise. We have unfolded them, and we see that that the corresponding trouble on the real number line is from left to right. Right, it's towards the positive numbers. Oh, yeah. What happened here? The opposite way or the same way? The same exact way, because again, the points are going to be specified 0, 1. You're going to see first 0, then you're going to see 1, then you're going to go to infinity, right? It does matter, of course. The effect of how the domain is parameterized will have the effect. Effect on the Mobius transformation and what it's doing to the interior. That's the last thing we need to discuss. So it's going to be the same way. 0, 1, and infinity, and we still, R still moves those points to the positive numbers like this. Alright, now complete this proof. You see what I have one Mobius transformation that unfolds one circle to the real number line, and the other unfolds the other circle to the real number line. Now, how would I map this circle to that? What do I need to do?
R4, W4.
You want to go?
Yeah, it would take. First map C2 to the Y under C, and then you take R inverse.
Good, wonderful. You see that. So we all see what you said. So you see what I do is R, you remember, Mobius transformations are invertible. If I can go this way, I can go in reverse. Right? I can go in reverse. So let's see. So we want, let's say, again, regardless of how you compose, let's say we want to go from here. We're going to go from here to here, and then from here to here. That's why it's R inverse. You understand? So all that is left for us to do is we just write our transformation T. Is going to be C composed with R inverse. That works. You agree on how it works? You see, just very visually, what I do is I take this circle. My first step, you see, the composition is this: take this circle, flatten it, and then once it's flattened, reverse. We have R flattened W. So now I reverse it, go back to the circle.
It's the opposite of how you wrote it, right?
Huh?
How you wrote it is the opposite, right? You mean R inverse C?
Yes, I guess so. Maybe first I go with C and then with R inverse. Thank you for noticing. I cannot tell left and right. My orientation is very unsafe for me, right? For me, it's like all the same. I used to in first grade write 16 and 61. It took me some time to figure the difference. But it's not terrible since I can see the difference. Some people never learn. I've seen people that in basic algebra, 2 to the power of 5 is the same as 5 to the power of 2, or the same as 2 times 5. Maybe there are other things going on, I don't know.
There's no commutative algebra.
So you kind of
Right, so you understand what I did, right? No need for that's the proof that one exists. How do you establish that there is only one? So if we established one exists, how do you know there is only one? Nothing else would work.
Mobius transformations are unique to your points.
Well, that's very good, right? So algebraically, we justify the fact that fixed points you can have up to two, or the identity. Either you have the identity function, or you have two fixed points at most, right? Now this will now if you select any other, I don't want to write. You can finish this proof, but if you select any other map that is carrying this circle onto this circle and carrying the z's onto the w's in this fashion, you can see that that by considering those two functions, by considering the composition of one function and its and the inverse of the other function, you will have the fixed points 0, 1, and infinity, pretty much, right? We already did it when we proved that that the cross ratio is unique. Yep.
Sorry, because I had to leave early last time. You only mapping to 0, 1, and infinity just for convenience, right?
For
It's
convenience,
always
no reason at all. I could have selected any other numbers. It's just the formulas would have been harder to establish. It's easy to see with the rational function what value it maps to 0, what value it maps to infinity, and a little bit harder, but still easy to see what it maps to 1. That's why you pick those numbers.
Okay.
You understand? Those are the best numbers for convenience, for the formula. You could have picked any other numbers. You could have tried to construct a similar argument when one circle is mapped to another, but that is complicated, right? Because then what are the formulas? How am I going to map one point to another? So with this, you can quickly see that I can map from one circle to another. That's the significance of the cross ratio. It's just merely that it's the simplest of the Mobius transformations that I can easily visualize. Okay? Maybe there are other significances, but as far as I would say, that's the immediate thing that comes to mind. All right. Now the last part is orientation principle. Right? That's the hardest thing for me. Maybe not for you. May I erase? And today we will hopefully begin integration finally. So I'm hoping you're not too disappointed. Yeah, I'm always worried about it. Orientation principle. So maybe we can phrase it in the following way. Let K1 and K2 be two circles in the infinity and T Mobius transformation. So it's a Mobius map such that T of K1 will be K2. In other words, it carries the circle K1 onto the circle K2. Let C2, C3, C4 be orientation. Be an orientation for K1. Then T takes the right side and the left side of K1, 1, 2, the right side and left side of K2. With respect to the orientation, TZ2, TZ3, TZ4. Now, a lot of words here. Let's try to understand what we mean. It's much simpler when you draw a picture for it. So here's really what's happening. So we have one circle, and that's the circle K1. And on that circle K1, I have orientation, so let me just draw the points. If you don't mind, I'll make them counterclockwise. So this is Z2, so I'm giving it a counterclockwise orientation. This is Z3, and this is Z4. So I'm walking this way. All right, so I'm walking counterclockwise. So I'm standing on this beam and I'm stretching my arms. So this here is going to be my left side. So you can think of this as left, right? And this as right. Because my right arm is pointing to that region, my left arm is pointing into the circle. Okay? Now, suppose that now the map T, this is the map T, and it carries K1 onto some other circle K2. This is another circle K2. So let's say that this time, this is my T of Z2. I just look at where Z2 went. So T of Z2 went here. And T of Z3 went here. And Z4 went here. So what did the map do? T of Z2, then Z3, then Z4, and so we now have clockwise motion. Yep. So this is now this is the image K2. Now, where do I write left? Where is my left now? Outside, exactly, right? So now my left arm is pointing outside. So this would be my left. And this inside of the circle is my right. Agreed? That's what this orientation principle is trying to put in words. We're going to maybe have 2 examples to practice that, and you have a homework assignment where you use it. It's a very useful principle. So why does it happen? It happens, I would say, there are many explanations, but a very simple explanation is this. A Mobius transformation is holomorphic. Right? It's holomorphic. So what I can do is, I can draw myself here. See, I can draw myself a stick. I can draw myself one directional vector and another to the left. Right? I have this thing. So the angles are preserved and the sense of the angle is preserved. That's very important, right? The sense of the angle is preserved. If it's anti-conformal like inversion, then the size of the angle is preserved, but the orientation of the angle, the sense of it, is reversed. So here I see that I move from this arrow, from the tangent arrow to the perpendicular arrow, let's say, I move counterclockwise. So to be inside, I take the tangent arrow, rotate it counterclockwise. That's what I have to remember. Now in this case, the tangent arrow has been migrated. It now points here, right? Now I need to rotate it counterclockwise to, you see, because the map is angle preserving, I would have to rotate this red arrow counterclockwise. So if it's in this position, it has to be rotated there. So that's really the proof of, that it's just a special case of holomorphic maps. Counterclockwise. Okay? Alright.
So does that mean that it's taking all the points inside the disk to when it
To the outside.
it maps it to the outside?
Absolutely, right? So, I mean,
And what if we have like what if that circle is not embedded in an ambient manifold, in an ambient space, and it's just a circle? But like if you look at a map from S1 to S1 without considering any embedding, where do the points on the inside? Well, I mean, there's no point on the inside.
well, I mean, again, with analytic manifolds, you would still, again, you would flatten them. You can flatten them to the complex plane and see what's happening there. Well, how would you define a holomorphic map from one manifold to another? You would have to create coordinate charts, right? So if you create coordinate charts, in essence, you can bring it back to that picture. Maybe something better can be said, but I do not know it well enough to tell you something better right now, right? But thinking about it in general, in principle, you can always think of it as locally mapping from complex to complex. Okay. So what else did I want to address? So very important idea is this, right? That where could the left go? The Mobius map is invertible, so it's both injective and it's bijective in essence, right? It's injective and onto. It's one-to-one and onto, right? And it's a continuous map. If you think of it as a map on the Riemann sphere, it's continuous everywhere, right? I mean, maybe we haven't dealt enough of it, but just write the equation. See that if you take z map is mapped to 1 over z, that's just the same as rotating the Riemann sphere. It's just a special rotation, right? So because of that, you see that any Mobius map is continuous everywhere. It's continuous at infinity. It's continuous at any point, and it's differentiable everywhere. And by continuity, the inside, and that, by the way, really confused the hell out of me. I once did a homework assignment for which I was marked absolutely wrong, because in real analysis, you see, it makes no sense to me, right? Because this is the bounded region; it's compact, right? So this region here is compact. If you put it together with the black circle, together the left plus the black circle is a compact region. So it made no sense to me that there would be a continuous map that could take left and map it all the way out. Right? But if you think of it as a map from the Riemann sphere to the Riemann sphere is compact. The unbounded region is just another picture of a compact segment. Right? So there is no problem in that sense. If you think of the Mobius map as a function from the Riemann sphere, it's again a manifold, right? So if you think of it from the Riemann sphere to the Riemann sphere, then there is no problem, right? So what is it going to do? Everything on the inside, it's a connected set, right? And it doesn't. It's everything that does not intersect, that is in the complex plane bounded, and does not intersect the circle. So where can it go? If part of it goes outside, then all of it must go outside. You understand? Because otherwise it would be disconnected by the circle. Make sense? I'm sorry if I'm just a bit loose about it. Does it make sense that if part of it goes outside, then all of it has to go outside? So that means that the image of the interior of this disk, it must be all the exterior. Yeah? Shake your head yes, or shake your head no if you fail to see what I'm
So
saying.
since you're saying that the Riemann sphere is compact, then
Yes.
it means that the point at infinity is not being excluded, right?
Yes, I mean if you think about this picture, if you think of the complex plane as really wrapped around the Riemann sphere, so if I think of it this way, right? So and I have the circle is this way. So we have the top hat is the unbounded region, right? So the top thing, this here is the unbounded region. I mean, maybe I put it in quotation mark because it is bounded, right? Okay, and it's connected. And this here is the bounded region. Okay, but on the sphere is a closed and bounded structure. It's compact. In other words, it has a finite size, if you will, right? it's a closed set in R3. So both parts are actually just connected, both parts, the top or the bottom part, you can think of them as connected and compact. I mean, of course, both of them have to then, if I say that the top is connected and compact, then it also takes together the boundary. It has to take this black line with it, right? So if I know that this circle is mapped here, then the green region, in the green region, part of it is mapped on the outside, the entire thing must be mapped to the outside. And since the function is onto, then the green must be coloring the entire outside of this circle. Do you see that? Okay. And similarly, by the same reasoning, then the right part, since it's moved inside, it's going to be completely covered. So this blue color must be filling the entire circle. Good? So let's consider basic examples. Example. So here is a circle, and let's just take Z2, Z3, Z4, and apply the cross ratio, CZ, which is Z, Z2, Z3, Z4. So the cross ratio will just take this region and unfold it. So this would be 0, this is 1, and this is infinity. This, now I'm going to shade the inside. What do I shade in response? Where do I shade here?
In the plane, you mean?
Yeah, in the plane. Where did the inside go?
Where are you mapping the CEI?
Well, by this formula it's clear. Again, I want to warn you that in Conway he's doing the opposite, right? So in Conway, this means slightly different. Okay, so it would be 1, 0, and infinity. In other words, you would go like this. And again, what also confused me, remember that this is infinity and this is also infinity. There is no minus infinity. It's slightly different picture. And if you go like this is also infinity. If you go like that, it's also infinity. Yeah. So where do I cover?
You didn't give an
To the
orientation.
left. To the left, so it will be
Again, I'm very terrible.
above.
Above. You're saying. All right. Who agrees? You agree it's above?
Indeed,
Well, yes, and maybe to the side as well. A little bit, right? Right. So let's try to understand how. So for that, I need to use orientation, right? I need to use the orientation principle that right away will tell me what's happening. So Z2, I like to start with Z2. So we go like this, like this, like this. Okay? We go, I made the picture counterclockwise. Okay? So here, it always, the way I oriented it, it always goes like this. Okay? Now it's now very easy to tell. What do I need to do? I need to look at the tangent line and then ask myself, where do I rotate my tangent line to be in the red region? Where do I rotate it? I rotate it, I rotate it counterclockwise, right? Right? Counterclockwise. So if I rotate it counterclockwise, here is the tangent line, I need to rotate it counterclockwise. So I must be mapping into the upper half plane. Okay? now given, I mean, in this example, we'll also give an explicit formula. This really was to me, just a few years ago, how is that, right? Because again, I'm trained, I've been, you know, some of you have seen me there, right? I have done a lot of real analysis, right? And I like real analysis, I kind of, it makes sense, right? And I was with absolute certainty saying that such a map is impossible, and I got 0. I couldn't understand how, right? How could I get 0 for my homework if I said that such map is impossible, which I know it isn't. But you understand why? In this new perspective, it is possible. You just change perspective. Now, you don't consider this unbounded. When you apply Mobius transformation, if you are going to say it's continuous function, otherwise, what do you mean continuous? What does it do? What is infinity otherwise, right? Then it's actually from the compact space. This is the image to keep in mind. There is no unbounded region. So this is inside, I said, together with this black line and red curve, so the black circle and the red meat of the interior is a compact set. And then I looked at this is not compact. Oh, it is compact in C infinity. That's the thing, right? It is not compact in C, but it is compact in C infinity, so everything's fine. Okay, makes sense? Okay, so we have this region. You see, nothing else is possible. I convinced you? Right? It has to be connected, and it's a one-to-one map. So it has to be the entire upper half plane. Now let me just draw another picture, and you tell me what happens now. Now I'm going to give clockwise orientation. So you see, so we have now again this will be Z2, this will be Z4, and this would be Z3. So I have clockwise orientation. And we have the interior of this circle is this. I apply the same C. Well, it's not the same. I mean, because I have different points, right? So Z2, Z3, Z4, and I have, again, we have 0, 1, and infinity. And again, the blue curve moves first to 0, then to 1, then to infinity. So again, we have this. Where is the interior of the circle map? Bottom half. You see why? Again, I look at the tangent to this the circle, and I know my map is conformal, right? In other words, it preserves the sense of the angles. So I rotate it from the tangent. I need to rotate it, in this case, clockwise, right? So I start here. I need to go clockwise, and if I go clockwise, I end up in the bottom part. Okay, good. And now finally, let's actually write an explicit formula, see if you can. You see, you can go in the reverse, right? If I start at the upper half plane, I can go into the inside of any circle. So let's now actually, final step in this example, let's actually have an explicit formula for, because that one is used rather often, of how to go from the upper half plane into the interior of the circle. So let's say, right? Explicit.
The target is going to be something like modulus C.
The what? Modules?
Yeah, the modulus C. I mean, for the image font, it's going to be something like modulus or whatever you.
I mean, you maybe a second. I'll just try it, and you'll tell me again what you have in mind. Write explicit Mobius formula for Mobius map from upper half plane So upper half plane, I don't need to explain what it is. It's all points where the imaginary value of z is bigger than 0. From the upper half plane into the unit circle. Or the unit disk, into the unit disk. Okay, so what we're interested in is we have the upper half plane. So it's here. That's the upper half plane. And I want a Mobius map that will, you see, this shows you that one should exist. This argument tells you that you should have one. Which, again, is very strange. And I want it to be mapped into so that's the unit.
So we said that the map was not only continuous but also surjective. The map.
Well, yes, the map is surjective because it's invertible, right? So of course it has to be both surjective and injective. And continuous, again, I can only make sense of continuity if I talk about the Riemann sphere, because I need to make sense of the point at infinity. And for the respect to the finite complex plane, well, I guess it's not continuous. Because it just kind of rips, it creates a hole, right? So if you map 0 to infinity, it's as if you take that's the way you would visualize it if it's in 2 dimensions, right? On a flat plate, it's as if you make a hole and you tear it apart and you kind of rip it out, right? So it's as if you make a hole in this paper and you pull its guts out, right? Which to me then it's not continuous. But then on the Riemann sphere, that's not what's happening, right?
Yeah, I was just asking because if we now go the other way, take a map from the upper half plane to the one dimensional, 2-dimensional disk, then we can probably get a continuous map, but it's going to be local. It's not going to be something surjective. Because otherwise, then we have the homomorphism.
But before you say local surjective, are you talking about a Mobius map? Because Mobius is always 1-to-1. It is 1-to-1 and it's always on.
This is bijective, right?
It's bijective because we can find a formula for its inverse.
And the inverse is also going to be continuous?
Well, the inverse is another Mobius map with the same properties. Yes. Okay. So the Mobius maps is just one specialty about this. It's not simple at all, by the way. I don't want to say it's very simple, but it's in terms of complex analysis, it's one of the simplest types of functions. All the others are either very trivial, like let's say AZ plus B is simpler, but all it does, it's actually also a Mobius map, but all it does is just moves the plane around and dilates.
But you see why I was asking that, right? Because if we have a map that is surjective and continuous from the 2 disk to the upper half plane, I'm seeing the upper half plane as the Riemann sphere, and then you have a continuous inverse, then you're saying that the Riemann sphere and the 2 disks are homomorphic. That's not possible.
Well, that's in essence was my problem understanding it, right? So I mean, but you see what is happening here. Really, how am I going to create such a map? If you look at Z4 here, I'm going to create a turning. You see, from the finite point of view, it's as if I cut this place, I cut it out, make a hole here, and then I spread it out. Understand? So if I had to do it, I imagine this is made of very stretchable rubber material, and I make it non-compact. How do I make it non-compact? I take scissors, and I cut this point out. Right? And where do I move it? I just unfold it to infinity. Right? So from that perspective, it doesn't look continuous. But from the perspective of the Riemann sphere, this is just moving this point to infinity is just ordinary rotation. Z mapping to 1/z is a way to move 0 to what do you call it? To infinity. And just by thinking of this Riemann sphere as a ball that you can just throw around, you can go anywhere, right? Just throw around anywhere. You can see that you can move any point to 0, and of course from 0 you can move it to infinity. Or just don't need to worry about it. You can move any point to the North Pole. So you can map any point to infinity. And all that it constitutes is just by simple rotation. You need to do more than just rotate this object. And by the way, I apologize, I actually forgot, I've seen this video before, but one of you have given me a nice 2-minute video that shows a very nice dynamic of it, right? So you can see how you think of the Riemann sphere and Mobius transformation of the Riemann sphere. I'm actually going to try to forward it tonight. Right, and another student, he did really nice inversions now in the sphere. Right. So really cool. All right, so I want to write an explicit formula. So here I just kind of used cross ratio and I didn't write an explicit formula. Now I would actually like to have an explicit formula for the specific instance of where I take the upper half plane and map it into the disk.
Can I take one guess? Just one.
Okay, go take one guess.
1 over modulo C e to the IC.
If you take modulus of z, you don't make it a holomorphic map, and that's the problem, right? So you might come up with another function that does that, but you don't want it to be. You want it to be holomorphic. So here's a very easy way to do that. You just fix. You can fix other points, but let us fix the point I. Not fix, just pay attention to the point I and the point minus I. And then I have the map f of z equal to z minus I divided by z plus I. Now why would that work? Let's now look at the modulus of this thing. So if imaginary part of z is bigger than 0, z is closer to I than it is to minus I. Do you agree? If I have a point, in other words, what I do is I select any point z in the upper half plane, and I'm going to show that it must be mapped into the interior of the disk, and that's because of that. You see, it's closer to I than to minus I. Do you agree? Yeah? So what it means very simply, how do I verify that it is inside? So, absolute value of f of z, which is equal to absolute value of z minus I over absolute value of z plus I, is less than 1, which implies f of z belongs to the unit disk. So how should we write unit disk? Maybe like this, d, which is d, such that absolute value of z, or the modulus of z, is less than 1. See here, let's do it out.
C the second time.
Huh?
C the second time. Instead of double, instead of all double.
Yeah, it's all the same, it's just so that you don't confuse with this z, right? So, I don't know. Not a big deal. Okay, makes sense? So this point had to be carried somewhere on the inside. How do you know it's onto? What you do is you first of all, you see, because this red region might be just smaller or some smaller shape, right? So maybe some sort of cloud inside. But the way you show that it's onto is now you can find the image of the inside and map it there. Okay. So we can find very quickly what's the formula for f inverse. So the formula for f inverse of z. Let's actually say f inverse of w, and the way to find this formula, what you will do is you look at the coefficient matrix of f of z. F of z has the coefficient matrix 1 minus I, and here we have 1 and I. And if I take this coefficient matrix, again, you can just do that by direct calculation. The reason this works, if you read, for example, even if you read visual complex analysis, you will read about homogeneous coefficients. You will understand that Mobius transformations can be thought of as quotient, as functions that arise when you take when you take projective space. When you take a space and you quotient it by one-dimensional linear complex spaces. And that will make it into, you can see that that's why we have matrix relation. So then all I need to do is I need to semi-find inverse of that matrix. What I do is I just will write I, 1, minus 1, and I. Sorry, so this is I, minus 1, this is I. Okay, which tells me that the inverse the inverse function at W will be I W plus I divided by minus W plus 1.
What do we say about the function? Because we only defined it and we said that the imaginary part was greater than 0.
No, I mean the function is defined on the entire complex plane, and in fact on the entire Riemann sphere, and I can find the inverse of that function here. Okay, that's the inverse function.
And the function is continuous, surjective?
It's again a Mobius map, just the same as the Mobius map above, but they're all creatures of the same family. So we have, this is the inverse map. Now here, if I now restrict this map to the region inside of the disk, now W is smaller than if I now look at F inverse restricted to the region D, implies that the magnitude of W is smaller than 1. Great. So it implies that magnitude of W is smaller than 1, and then I can just investigate the equation of F inverse W and see that for those W it's going to be the upper half plane. What I can do is W plus 1 over minus W plus 1, and what you can do, you can create a positive denominator by multiplying by the conjugate. What you have is plus 1, and when you just expand it, just continue this expand it, you will see that the imaginary part, if you just write it basically as a real part plus imaginary part, you will see that the imaginary part is bigger than 0. Okay. So I just gave you just an outline what you can do, right? So this would now make the denominator positive, right? And then then you just multiply it out, and then W is x plus iy, and you would find that the y would have to be positive. Okay. I just want to finish today the Mobius map, and I want to still give you 2 more examples. How that might be working. One example is similar to what you would have in the homework, so I thought maybe I'll example. So we just want to understand the action of the map. So we have T of Z is 1 over Z minus A. And we want to apply this map to the following picture. So we have, so this is A. And we have two circles that are touching at A. So this is A. And two circles are touching at A. Okay? And I want to know what's going to be the image under the action of T. Okay? So let's also try to give those circles orientation. First of all, let's break it apart into our regions. So we have this region and we have that region. And let's say that they are both counterclockwise. So I give those circles counterclockwise orientation. So where is A mapped by this Mobius map? To infinity, right? Now, let's see.
Where's A in the picture?
So let's try to understand what happens to this region I.
What point is A? The one where the
Where they touch. That's where they touch. Okay, so they are tangent circles at A. So A is mapped to infinity, and then what is the map going to do? So so what is it first of all going to do to this circle? Think about it. What's going to happen to this small circle? First of all, what shape is it going to have after I apply Mobius map? You can do it. No? Big hint. Part of the circle, one point of the circle, where is it mapped? The circle contains the point A. And where is A mapped? To infinity. So it's going to be a line, right? Now this line, look at this red curve. The red curve goes right in the middle, right? The idea is that I drew you a red curve that goes right in the middle of the circle. So what can you say about this angle of the circle to the red line? Yes, and what would that be in particular? What's the value of that angle? 90. This is a right angle. So if I track where the red line is going to go, so again, I didn't specify what A is. A could be complex, but if A is real is one thing. If A is complex, then the line will. I'm not saying this is the x-axis, right? I'm saying that this red line is going to be mapped again to a red line. Now, this is very similar to inversion. You agree? Very similar to inversion. So what is it? If I just map this red line under inversion, it's going to be itself. And if I take conjugate of that line, again, if it's horizontal, then I can actually I will need to track where that red line goes. If it's actually the x-axis, it will just stay horizontal. If it's not the x-axis, then it would be, again, the way I do it, let's say it's the x-axis. Let's say that A is some real number. Take it to be even 0 if you want. But in general, I would need to track where this red line goes. I don't know. I need to know something about A. So this is that red line. it's horizontal. Okay. Now, inversion, right? You see now, if you think about it, take the conjugate, it looks like inversion. What is it going to do to those circles that are tangent at this point? It's going to map them into straight lines. So with the same direction, right? If it's inversion, it will be the same direction. And the smaller this circle is around the infinity point, this is the infinity, the farther is the line. So this line here is going to be, say, it's going to be mapped in here. And it has to be vertical. And so this would be, let me make this color for you. So this line here is carried somewhere here. Okay? What can you tell me about the orientation? Here it's counterclockwise. What can you say is going to happen? Very important. Because we would want to find what happens in between. So I need to know what happens to the orientation of the line. Down, brilliant, right? Now how do you know it's down? Take inversion. Inversion will be just the line will be moving up. You see, just take the inverse image from some circle, right? The circle that's centered at A. Take any circle centered at A and take the inversion, and that would map to a line, and it would be moving up. But because we need to then take another conjugate, it's going to be pointing down. Brilliant. So we have it going down. See, I was sure I'm going to cover integration. I was certain. Actually, I thought that I didn't have enough notes, right? Okay, so this is what's happening to that green line. Now, please tell me what happens. Do I have a little bit more time? Yes? What happens to the other line? What happens to the other line? Where is it going to be mapped relative to this line?
Closer, but then down.
Closer, right? The bigger the circle, the closer. Do you see that? Right, and also pointing down, right? So, I don't know which should I use, maybe this color. So it's going to be mapped closer. I don't know exactly where, but closer. And what can you say about orientation? It's also down. Okay, good. So you see the bigger circle is mapped closer to the orange. Because it's like 1 over r, right? Making sure there are. All right, so then what's going to happen to 1? What's going to happen to this green circle if I now color it? Where is that going to be? Wrong?
Oh no, it's gone. I didn't see the arrow now. Oh, left.
To the actually right.
To the right.
Right. So it's going to go here. Do you all see that? So that's where region number 1 goes. And by the way, if I were nitpicking, the top part of this region, so the one above the red line, is it going to go above or below the red line? Below. Very good, right? And if I just change this like this, then that would be here. A little bit nitpicking, but you understand, right? So you can see where it's going. So that's region number 1. What about region number 2?
Now what is it?
Yeah, they must be between. You see why? Because again, where can this region go? It must be outside of this green circle. Therefore, it must be closer to the blue line. Right? It might be not here. It must be somewhere here, right? And it cannot exceed this blue line, so it must be here in between. So this here is region number 2. All of it, right? With the top part being mapped to the bottom. We just flip it, right? Do you see why? Inversion will kind of carry it directly, and if you need to take for inversion, you need to take double conjugate. So to take the conjugate inversion, so you just do this with the picture. So it's like inversion, but just do this. Okay, and then finally, with whatever is above the blue line, but below this, let's say this red line. Where is that going to be mapped? So region number 3 is here. So where is that region? So the region number 3 is in the right half plane. Where is it going to be carried? It's going to be carried in here.
Yeah, that one.
Right? So here. Between the red and this blue line. Of course, again, I want to emphasize that I don't know. I mean, if A is complex, then this picture, this sideways T might be slanted, right? If you just take this, rotate it a little bit, and that would be correct, right? If with respect to the horizontal, A is pointing this way, then this will point this way. It's just because what you do is you take inversion and then you rotate again. I have one more example, but I think I will not finish it today because I don't have time, right? It's a bit long. I don't want to show it. You see it here, I worked on it. This, by the way, maybe you would say, well, there's a very easy proof, but I once was asked to tutor something in geometry. I don't have any formal knowledge of geometry, so I thought, how do I establish this fact? And I just thought Mobius Transformation, right? and I'm hoping that you will not say, oh, something is wrong. I'm sure they're going to say, but there's a very easy way to do it. Maybe.
Is this from the visual complex, most of this stuff?
Well, I mean, Mobius transformations are covered very well in visual complex, yes.